In yesterday's lecture, we saw that we looked at the superconducting transition as in terms of the Ginzburg-Landau theory, and we wrote a free energy for the superconducting state and then minimize the free energy to get Ginzburg-Landau equations. So these were two equations that we had derived, and now we will see as we go along the consequences of these two equations, where we had minimized the free energy with respect to the order parameter, which is taken as psi naught e raised to I phi. The order parameter psi is taken as equal to psi naught e raised to I phi, where psi naught is proportional to your Cooper pairs, the density of Cooper pairs inside the system, and phi is the phase. Okay. And we also take a look at the vector potential, minimize it with respect to the vector potential. And when you do these two minimizations, one with respect to the vector potential and one with respect to the order parameter, you will land up with two GL equations. And that is what I will just recall. Earlier I had made a sign mistake in one of the GL equations. I will just correct it. So I will write down the GL equations once again, and there might be a slight change with respect to the earlier equation because there was a sign mistake in one of my equations which I had written down last time. So let me write down these two GL equations. So the order parameter is psi naught e raised to I phi, where phi is the phase of the superconducting state. So the entire superconducting state is treated with one single phase phi, and psi naught square is basically the density of Cooper pairs. In the superconductor, and the free energy of the system is written as a function of psi as well as the vector potential A, which we had written down, and then you minimize the free energy by taking psi going to psi plus delta psi, and you also minimize the free energy by A going to A plus delta A, the vector potential. And then if you do this minimization, you get the first GL equation, which is basically IH cross del plus 2EA the whole square psi plus alpha psi plus beta psi square psi is equal to 0. This is our first GL equation, and I think I had made a mistake here. Instead of this is actually plus. I think I had written it minus in my earlier expression, so please correct it. In my earlier lecture I had written this. So minimization of the free energy, when you take the minimization of the free energy by psi going to psi plus delta psi, you have the first GL equation, which is written like this. Okay, this essentially represents the momentum kinetic energy, and 1 by 4m. Okay, so this is essentially the kinetic energy term. Okay, and p square by 2m, where the canonical momentum is p minus ea by c, where the charge is now 2e. So this will basically give you your first GL equation, and you can rewrite this as minus h cross square by 4m minus h cross square by 4m and del minus 2IEA by h cross into vector potential the whole square psi plus alpha psi plus beta mod psi square psi is equal to 0, or you can also rewrite it as 1 by 4m h cross square del square minus 4IE h cross a bar gradient of psi del square psi minus 4E square a square psi minus alpha psi minus beta mod psi square psi is equal to 0. So these are different forms of the first Ginzburg-Landau equation. All of them are equivalent. You can use either one of them. Okay, these are all equivalent forms. And the second GL equation, which you can get by minimizing, when you minimize it with respect to the vector potential, is the second GL equation, and that is relating to the current density J in the system, okay, which is minus I H cross E by 2m psi star gradient of psi minus psi gradient of psi star minus 2e square by m vector potential A mod psi square. This gives you your current density in your superconductor. So these are the two GL equations which you can now describe the superconducting state. Okay. So the case 1 that we will consider first is, so now we look at the consequences of this. Okay. So the case 1 is zero field, a superconductor in zero magnetic field, a superconductor kept in zero magnetic field, namely the vector potential is taken to be equal to 0, and because there is no magnetic field applied, the current density is also 0. Because if you don't apply a magnetic field, there are no shielding currents generated around the superconductor, so you don't have any current density in the system. So the second GL equation implies that psi star gradient of psi is equal to psi gradient of psi star, where psi is psi naught e raised to I phi. Okay, and this psi star gradient of psi equal to psi gradient, if I substitute this into above equation, then I will land up with the condition that I mod of psi naught the whole square gradient of phi is equal to minus I mod of psi naught the whole square gradient of phi. Now mod of psi naught square is not equal to 0 because density of Cooper pairs inside the system is not equal to 0. If it's a superconducting state, definitely mod of psi naught square cannot be equal to 0. So the only way the above condition is satisfied, only way to satisfy above condition is that gradient of phi is equal to 0, or phi, the phase phi is not a function of position in the superconductor. The phase phi is not a function of position in the superconductor. So as you move across the superconductor or as you move into the superconductor, the phase phi does not vary at all inside the superconductor. So this is the first condition, that phi is not a function of position in the superconductor. This we have derived for this case. Okay. Now with this in place, let us go further and look at your first GL equation. So now our first GL equation with these conditions becomes, in the first GL equation we put the vector potential A equal to 0 and then minus alpha psi minus beta mod psi square psi plus 1 by 4m h cross square del square psi is equal to 0. So this is your first equation where we have put our vector potential A equal to 0. Okay. Now since the phase phi doesn't have any spatial dependence, the entire part of the spatial dependence will be in psi naught. Okay, so the spatial dependence will be in psi naught because there is this term. So there is going to be some spatial dependence of psi. So because this phase does not have any spatial dependence, it implies that psi naught in psi equal to psi naught e raised to I phi. It is psi naught which has some spatial dependence. And now psi we write it as psi naught into f, where f, the function f has all the spatial dependence of psi. The function f has all the spatial dependence of psi. Okay, and psi naught, if you recall from general GL considerations, is equal to minus alpha by beta. If you minimize your Ginzburg-Landau free energy functional, we have seen that psi naught square is nothing else but the equilibrium value. This we had worked out in the general expressions of that it will turn out to be minus alpha by beta, where alpha is equal to A T minus Tc. Okay, this was the temperature dependence of alpha. Okay, so below the superconducting transition, below Tc, minus alpha is equal to A Tc minus T for T less than Tc. Okay, so psi naught square is equal to minus alpha by beta, which is basically A Tc minus T by beta for T less than Tc. Okay, so this is the valid behavior of, this is the temperature dependence of psi naught square. Okay, now let us look at this spatial dependence. Okay, let us look at the spatial dependence. Let us look at the spatial dependence of psi, spatial dependence of f as one approaches a superconducting boundary. Okay, so we will try and look at the spatial dependence of this function f. Recall this function f psi is equal to psi naught into f, where f contains all the spatial dependence of the wave function psi, of all the order parameters psi. F contains all the spatial dependence of the order parameter psi. So let us look at how it is going to behave as one approaches a superconducting boundary. So let us consider a 1D case where for x less than 0, one has vacuum. Okay, so for x less than 0, one has only vacuum, and for x greater than 0, one has the superconductor, namely here everything on this side is the superconducting state. This is x greater than 0, and everything on this side is vacuum. Okay, so you have a superconducting state on this side and you have vacuum on the other side. So how is the order parameter going to behave inside the superconducting state? Okay. So let us, for the 1D case, your equation that we had written down, let me rewrite that equation. Minus h cross square by 4m del square psi plus alpha psi plus beta mod psi square psi is equal to 0. Okay, I am just taking the signs again. Okay, and for 1D case, one dimensional case, this is nothing else but minus h cross square by 4m d square psi by dx square plus alpha psi plus beta mod psi square psi is equal to 0. Now psi is equal to psi naught into f. So if you put that here, you will land up with the expression minus h cross square by 2m by 4m d square f by dx square plus alpha f plus beta f cube mod psi naught square is equal to 0. So once you substitute this here, you will land up with this expression where now mod of psi naught square is minus alpha by beta. So basically you can write this expression as minus h cross square by 4m d square f by dx square plus alpha f into 1 minus f square is equal to 0. Or you can rewrite this as minus h cross square by 4m alpha d square f by dx square plus f into 1 minus f square is equal to 0. This is one equation. Okay. So we are basically trying to solve this. We will try and solve this differential equation as it approaches the boundary. How does this equation behave near to the boundary between the superconducting vacuum interface, and how does it behave far away from the interface? So how does this equation behave? Near the boundary of a superconductor vacuum interface and far away from it. Now, if you look at this above expression, one can non-dimensionalize it. This is something you know, that if you have a differential equation here, these are dimensionful quantities. X is has dimensions of length. Now you can non-dimensionalize it. Okay, and you basically can by defining a parameter which is xi square, which is minus h cross square by 4m alpha. Okay, where alpha is equal to a t minus tc. Xi square is nothing else but h cross square by 4m a tc minus t raised to minus 1, or alpha xi square is h cross square by 4m a raised to half tc minus t raised to minus half. Okay, so this is a length scale, and your equation 1 can be rewritten as xi square d square f by dx square plus f into 1 minus f square is equal to 0. Okay. Now if we define a parameter eta is equal to x by xi, then it will non-dimensionalize the above equation. You can express it in terms of this non-dimension parameters. This has dimensions of length. Okay, so basically you can make it non-dimensional. Okay, where if I substitute this here into this above equation, I will end up with d square f by d eta square plus f into 1 minus f square is equal to 0. Okay, so then we will interpret what is this length scale xi. We will look at the interpretation of xi length scale, okay, which will help us to find. Okay, so we will do that in the next lecture.